And MDUF vibrations, specifically of classically damped systems. We considered some NDOF system as shown here, and then we showed that we could replace this system into matrix form, where we'll have, for our mass matrix, we'll have M1, 0, dot, dot, dot. We'll do that in a moment. 0, M2, then dot, 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 0, dot, 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 0. Zeros down here. To Mn. So this is our n by n mass matrix multiplied by the n by 1 acceleration vector. So x1 double dot, x2 double dot, dot dot dot, xn double dot, plus, for our damping matrix, we'll get C1 plus C2 minus C2 minus C2 and we'll get here C2 plus C3 plus C4 dot dot, get 0, 0, 0. Then lastly, we'll have Cn plus Cn plus 1. All of that multiplied by the velocity vector x1 dot, x2 dot, up to xn dot. And then we'll just add some annotations. This is our mass matrix, or capital M. This is an n by n mass matrix. This as well as our damping matrix, or our n by n, capital C n by n damping matrix. X double dot here is our n by 1 acceleration matrix, or vector. And then x dot, n by 1 velocity vector. And we got lastly the stiffness matrix times the displacement vector, and then the external forcing vector. So plus the stiffness matrix, we're going to get K1 plus K2 minus K2 minus K2 Oh, and let me make a correction here. There should not be a C4 up there because we don't have a, I thought we had a grounding stiffness or a grounding damper shown here as well, but we don't. So it should be C2 plus C3. And then over here, we're gonna have K2 plus K3, dot, dot, 0, dot, 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 0. Down here, we get a 0. Down here, a 0. And then lastly, we'll get Kn plus Kn plus 1. All that multiplied by the displacement vector x1, x2, dot, 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 xn, and equal to the forcing vector, which will be f1 of t, f2 of t, up to fn of t. So lastly, we have our stiffness matrix, or K, capital K, which is an n by n stiffness matrix. X will be the n by 1 displacement vector. And then lastly, f of t here is the n by 1 forcing vector. We can write this in a reduced form where you have m x double dot plus cx dot plus kx is equal to the external forces f of t. All right, we then talked about classical versus non-classical damping. Classical damped systems possess normal modes or classical normal modes that are identical to those of the undamped system. Non-classically damped have complex modes or modes that are different than the undamped system. And the way to determine whether a system is classically damped is to check the following, if the following is true, where we have the m inverse times k, that quantity times m inverse c. This must be equal to m inverse c times the quantity m inverse k. The system is classically damped if and only if this is true. We did talk about Rayleigh damping at one point. That is a type of classical damping and it satisfies this equation. It's not a condition though. Because you can have different types of damping that does not satisfy Rayleigh damping but is still classically damped. All right, we'll now take a look at modal analysis of classically damped systems. So when we're dealing with classically damped systems, the undamped normal modes are the same as if the system were undamped, and then they will ultimately allow us to diagonalize the damping matrix. A general procedure is to compute the normal modes, which includes the natural frequencies and the mode shapes for this undamped, unforced system. To do that, we're going to end up solving the equation k minus omega squared m times a vector x is equal to 0. By solving this, we will end up finding our natural frequencies, omega I, as well as the mode shapes, which we'll say is x sub I. To find the natural frequencies, we've got to take the determinant of everything in that parentheses and set that equal to 0. Then once we find the natural frequencies, we can plug them into this equation and then solve for each of the values of the mode shape. From there, we're going to want to mass orthonormalize our mode shapes. To do that, we're going to say that lowercase phi, which is our mass orthonormalized mode shape, is going to be equal to some parameter alpha I times xi. And we're going to do this for every mode shape. And then we'll form a modal matrix. Capital phi is equal to a matrix composed of the mode shapes where each column is a mode shape. Phi1 up to phi n. Once we have done that, and if we've done this correctly, then the modal matrix capital phi transpose times m times phi, this will be equal to an identity matrix. And then phi transpose k times phi, this will be equal to a diagonal matrix of the natural frequencies squared. And then we're going to add one more to this. And when we apply this to our damping matrix, so phi transpose c, phi, this will be equivalent to some diagonal matrix 2 zeta sub I times omega I. If you have Rayleigh damping, then you can substitute in for the stiffness and mass matrix into your damping matrix, and then apply the identities, the first two identities. You combine those together, you'll end up setting that equal to 2 zeta omega I anyway. All right, from here we're going to want to go and define modal coordinates. This is where we'll say that the vector x is going to be equal to the modal matrix phi multiplied by some modal coordinate vector. And then we're going to use that to decouple the equations of motion. Specifically, we are going to substitute that into our equation of motion and then pre-multiply by phi transpose. And then this will give us that phi transpose m phi eta double dot plus phi transpose c phi eta dot plus phi transpose k phi eta will be equal to phi transpose times f of t. And then we'll compute normal initial conditions, eta of 0 equal to phi transpose m times x is 0, and eta dot of 0 will be equal to phi transpose m times x dot of 0. So in our equation of motion, the first set of matrices is going to reduce down to an identity matrix. The second set is going to reduce down to that diagonal matrix of 2 zeta I omega I. And then the last bunch here is going to reduce down to a diagonal matrix of omega I squared. And then lastly, we're going to get what we'll call the modal forcing, which we'll just say is a vector capital N of t. Okay, from here, we'll end up with a second order ODE for every mode, or every modal coordinate, of the form eta sub I double dot plus 2 zeta I omega I times eta sub I dot plus omega I squared times eta I. And then this must be equal to Ni of t, and then we'll have some initial conditions, eta I of 0 equal to h sub I, and eta dot sub I of 0 equal to a g sub I. All right, from there we're going to want to solve for the free and forced response of the modal oscillators. We're going to find then that n sub I of t will be equal to e to the minus zeta I omega I t times the quantity h sub I times the cosine of omega d sub I times t plus fraction g sub I plus zeta sub I, omega sub I, h sub I, all of that divided by omega sub di times the sine of omega d sub I t plus some particular solution, eta sub pi of t, and that is going to depend on whatever the forcing is applied to the system. So that is not something that we can write out as a generic, or we can write out a set formula for. It depends on the forcing. This first component here, that's our free response. And then the second portion, we can call that the forced response, or we could also call it a particular solution. And here, this omega sub di, this is equal to omega I times the square root of 1 minus zeta I squared, where we've gone ahead and we've assumed the system is underdamped, or each mode is underdamped here. If they are not underdamped, then you need to go back and look at what we did for single degree of freedom vibrations, what the solution was for critically damped and overdamped, and then use those instead. All right, from here, we are going to perform modal superposition to form our final solution. And what that means is that we're going to go back to where we said x of t is equal to phi times eta of t. This is our modal superposition. And so this will be that we'll have x sub I of t is equal to lowercase phi sub 1I times eta 1 of t plus plus phi sub I times eta I of t plus plus phi ni times eta sub n, where I here is equal to 1, 2, all the way up to n, and that is the displacement of the ith coordinate. And this is what we mean by modal superposition. All right, we'll move on to the Laplace transform. So the Laplace transform, which we wrote using a script L, applied to some function at time f of t. This is equal to some function of the complex variable s, and this is defined as the integral, at least we defined it to be the integral from 0 to infinity. You can also define it from minus infinity to infinity of e to the minus st times f of t dt. And then we define our inverse Laplace transform. We used script L with a superscript -1. This is applied to one of these, a function of s, And then this gives us back the corresponding time function. And we didn't go over what the actual integral definition is for the inverse Laplace transform. So for two functions, f1 of t and f2 of t, the Laplace transform of their summation is simply going to be the Laplace transform of the individual parts. So we'll get Laplace transform of f1 of t plus f2 of t is equal to Laplace transform of f1 of t plus the Laplace transform of f2 of t, such that we can break up this into components and then compute Laplace transform of each component and go from there. All right, so here's a table of common Laplace transform pairs. This is the table that you were given on the midterm. This is the table you'll be given on the final if you need one. There are many, many, many more Laplace transforms out there in general. These are just the ones that we might see in an exam. All right, we're going to move on to partial fraction decomposition. So partial fraction decomposition allows us to compute the time response of some complicated Laplace transform using the inverse Laplace transform of a set of simpler functions. In order to do this, we must have the function in factored form, where f of s is equal to some fraction b of s divided by a of s equal to, go back to our fraction here, we'll have the gain k in the front times s plus z1, that's our first zero, times s plus z2, second zero, dot, dot, dot. All of that multiplied by s plus zm, where that's the mth zero. And then in the denominator, we'll have s plus p1, first pole, times s plus p2, second pole, dot, 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 multiplied by s plus pn, where that's our nth pole. And generally, we're going to see cases where n is some integer greater than m. If m is greater than n, then we actually have to go and do the division, and then we'll do partial fraction expansion on the remainder of that division. We looked at a couple different cases. The one that really popped up, or there were two that popped up the most. The first is where we had distinct poles, and the second is where we had some quadratic factor. We'll cover distinct poles first, and then we'll talk about the quadratic factor. So for distinct poles, we'll have f of s equal to b of s over a of s, which is then equal to some function a1, or some constant a1 divided by s plus p1, plus a constant a2 divided by s plus p2, plus dot, 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 plus some function an divided by s plus pn. And then we can solve for these constants. A, we'll say a sub I should be equal to the quantity s plus p sub I times b of s divided by a of s. All of that evaluated at the pole s is equal to minus p sub I. All right, so from there, we can go and find the time response using our inverse Laplace transform. We'll apply that to each portion of this partial fraction. So the inverse Laplace transform of a sub I divided by s plus p sub I. This is going to be equal to a sub I times e to the minus p sub I t, such that f of t here is equal to the inverse Laplace transform of f of s, which will then be equal to a1 e to the minus p1t plus a2 e to the minus p2t plus dot 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 plus an e to the minus pn t, true for or valid for t greater than or equal to 0. And then just as a note for the final exam, you can use a different technique for finding the partial fraction decomposition, but if you get that wrong, which many of you did, then we're not going to be able to check your work and you're going to lose more points as a result of that. We won't be able to go and find your errors and figure that out. There's just simply too many of you for us to do that. But if you use a different technique and you get it right, then that's not a problem. Because generally we'll look at the final answer and work backwards when we grade these things. So if you get it right, then it doesn't matter what you use. All right, so if f of s has a quadratic factor, such as s squared plus a times s plus b, with pair complex roots specifically, then we're going to want to expand this in a way that lets us lets us obtain sines and cosines in the time response. So just as a short example, if we have f of s equal to something like d of s plus e divided by s squared plus as plus b, we're going to want to expand this d times s plus e, s squared plus as plus b. We're going to want to expand this into something like x1 times s plus alpha divided by the quantity s plus alpha, that quantity squared, plus omega squared, plus some x2 times omega times s plus alpha, that quantity squared, plus omega squared. Then we can go and compute the time response. We'll find that the inverse Laplace transform of x1 times s plus alpha divided by s plus alpha quantity squared plus omega squared plus the inverse Laplace transform of x2 omega divided by the quantity s plus alpha squared, alpha quantity squared plus omega squared. This will be equal to x1 times e to the minus alpha t times the cosine of omega t plus x2 e to the minus alpha t times the sine of omega t. And then if you end up with a problem with repeated roots, you'll need to see how to deal with that as we did in chapter 4. See example 4 in chapter 4. All right, we're going to look at how do we solve linear time invariant ODEs using this technique. There's a general problem solving technique. The first is step 1, we're going to convert our ODE into an algebraic equation in S. So we're applying the Laplace transform to that ODE. And this is going to give us an algebraic equation in S. From here, we're going to solve for the dependent variable. From there, we're going to want it to expand using partial fraction. And then lastly, we're going to want to compute the time response using the inverse Laplace transforms. All right, moving on to chapter 5, where we looked at transfer function modeling. We're going to consider an LTI system, or a linear time invariant system, of the form A0 times dn y over dtn, so that's the nth derivative of y with respect to t, plus a1 d to the n minus 1 y over dt to the n minus 1, plus plus a to the n minus 1 y dot, so that's now our first derivative, plus an y is now equal to b0 dmx over dt to the m plus b1 dm minus 1x over dt raised to the m. So the m minus 1 derivative of x with respect to time, where x is going to be our input, plus plus b m minus 1 x dot plus bm times x, where y of t is the output of our system and x of t is the input to the system. From here, the transfer function, we can compute, we'll just say Tf here is equal to g of s, which is going to be equal to the Laplace transform of y of t divided by the Laplace transform of x of t. We're assuming 0 initial conditions. And then this is equal to big X over, sorry, it should be big Y of S over big X of S. Which would then be equal to big fraction with B0 times S to the M plus B1 times s to the m minus 1 plus plus b sub m minus 1s plus bm. And then divided by a0 s to the n plus a, that should be b1, a1 s to the n minus 1 plus plus a n minus 1 s plus a n. And then the inverse Laplace transform of g of s here is called the impulse response function. So it's the response of the system to an impulse applied to it. All right, I'm going to move on here. All right, so in chapter 6, we dealt with state space modeling. We first defined what a state is, a state vector, and what state space is then. I'm going to do that now. So the state is, or the state of a dynamic system is the smallest set of variables needed along with the input to completely determine the behavior of the system. And these are called the state variables. So the state of a dynamic system is the smallest set of variables needed along with the input to completely determine the behavior of the system. And so this set of variables is called the state variables. All right, so then the state vector is a vector whose components are simply the state variables for a given system. So a vector whose components are the state variables for a given system. And the state space is just the n-dimensional space that contains all of those state variables. So if we have n state variables, or for 4n state variables, the state space is the n-dimensional space containing those vectors, we'll say, or containing those variables. All right, and this then brings us to the state equation and then the output equation, which we'll write out and then we'll be able to put into matrix form. So for our state variables of x, we'll have x1 dot is equal to some a11 x1 plus a12 x2 plus dot 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 up to a1n xn plus b11u sub 1 plus b12 times u2 plus dot 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 plus b1 r ur then dot 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 all the way up to xn dot is equal to a1n x1 plus a, this should be an1 an2 x2 plus dot 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 plus ann xn plus bn1 u1 plus bn2 u2 plus dot 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 plus bnr ur. That's our set of state equations. So there are n of them. And note here that r is the number of inputs, and that does not have to equal to the number of state variables. So you can have more or fewer inputs than the number of state variables. And then our output equation is going to be y1 is equal to c11 x1 plus c12 x2 plus dot 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 plus c1n times xn plus d11 times u1 plus d12 u2 plus dot 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 plus d1r ur, and then dot 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 y, in this case ym. This is going to be equal to c m1 x1 plus c m2 x2 plus dot 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 plus c mn xn plus dm1 u1 plus d m2 u2 plus dot 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 plus dmr ur. Or in matrix form, we can write this as x dot vector is equal to the matrix A times x plus B matrix times U, and y dot, or actually that's just y. Y is equal to the matrix C times x plus matrix D times U. All right, we're going to move on and take a look at the transfer function matrix. So we're going to consider a multiple input, multiple output system. We're going to assume that there are R inputs, U1 up to UR, M outputs, just like we had above. We're going to write here, just as a reminder, our U vector is equal to U1, U2, up to UR, that transposed. Output vector y equal to quantity y1, y2, up to ym. The transfer matrix G is going to relate the output of y to the input u through the expression y of s is equal to G matrix of s times the input vector us, and here G of s, that matrix, is going to be equal to the C matrix times the quantity S times the identity matrix minus our A matrix or system state matrix, all of that to the inverse, times B plus the direct transmission matrix D. All right, now talk about solutions for non-classically damped MDOF systems. We'll consider just an MDOF system here where we'll have M times X double dot. We're going to drop the matrix notation with MX double dot plus CX dot plus KX is equal to a forcing vector FT, and then here X 0 is equal to some constant A, where A is a constant vector. X dot of 0 is equal to some constant vector of B. And then here we'll find that the equation m or m inverse times k times m inverse c. This is not equal to m inverse c times m inverse k. So that those quantities do not commute, and therefore the system is not classically damped. From here, we're going to convert into state space form. This will give us z dot is equal to a z plus, we'll say g of t here. G of t here is not a transfer function. It is a state space form of the forcing vector. Z here is going to be equal to the vector of displacements and vector of velocities stacked up together like that. Displacements first, velocities second. The matrix A, in this case, is our system state matrix. It's going to be composed of the following. We're going to have a big zero matrix up in this left corner. We'll have an identity matrix to the top right. In the bottom left, we're going to have minus m inverse k. And in the bottom right, we'll have minus m inverse c. And then lastly, this vector g of t, this will be equal to a vector of 0, and then m inverse times f of t. So that's the state space form for this system. There is no output because the output, the output of this is the displacement x, and so you can determine what the output matrix is for that. It's going to be an identity matrix or some form of an identity matrix, so as a result, we won't actually consider that. So this is a first order ODE. We can write out the solution as z of t is equal to some, e raised to the matrix A times t. Here I am going to put the matrix notation just so that we are aware that that's a matrix exponential times the vector of initial conditions plus the integral from 0 to t of e raised to a times t minus tau times force g tau d tau. All right, we have two solution methods for solving these equations. First is modal analysis using left and right eigenvectors. The second is an expansion of this matrix exponential using Cayley-Hamilton theorem. So first we have modal analysis using left and right eigenvectors. And then second, we have an expansion of the matrix exponential using the Cayley-Hamilton theorem. Which states that every matrix will satisfy its characteristic equation. All right, with that, we're going to take a look now at chapter 7, which focused on frequency response and Bode diagrams. So first, the frequency response function is related to the transfer function via the substitution of S is equal to J omega. So if you find your transfer function, G of S, then you can substitute in there S is equal to J omega, and then this will give you your frequency response function, H of omega. For an MDOF vibrating system, the FRF is going to be an M by N matrix, where M is the number of degrees of freedom, N is the number of inputs to the system. And then for a MIMO state space system, the FRF is an M by N matrix, where M is the number of outputs, and N is the number of inputs to the system. All right, we looked at Bode diagrams next. Bode diagram consists of two graphs. First, a curve of the log magnitude versus the log frequency. And then second, a curve of the phase angle versus the log frequency. So a curve of the log magnitude versus log frequency. And then second, a curve of the phase angle versus the log frequency. All right, the log magnitude is plotted using the decibel scale. This is 20 times the log base 10 of the absolute value of our frequency response function. And then the Bode diagram of a constant is just a straight line magnitude, and it has zero phase. Integral terms will produce a straight line with a slope of minus 20 dB per decade. Have those shown on the right there. And then on the left here is the Bode diagram for a first order system. Well, it says right, but it's on the left actually. Correct that. All right, so we're going to be approximated using two straight lines that connect at the corner frequency. Corner frequency is where the phase is equal to pi over 4 or 45 degrees, negative 45 degrees specifically. We discussed the asymptotics in detail. We're going to move on to second order system. This is the Bode diagram for a second order system shown to the left here. It is the same as what we saw in chapter 2, except that now it's plotted on a log frequency scale. And in this case, the asymptotes are much harder to use to analyze the system. Just for reference, the asymptotes are lines that look like the following. Straight horizontal line like that, and then a slope line looking like that. And so depending on what your zeta value is, the response may be very far away from that corner frequency. All right, and that is everything that we